How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at density and molar mass of an ideal gas. Our objectives will be to apply the ideal gas law equation to solve for the identity of a gas based on its density and vice versa. If I gave you density, be able to figure out potential identities for what that gas is. So let's get going. So we know PV equals nRT, right? That's the ideal gas equation. We also know that the number of moles is equal to grams divided by GFM. So if we were to plug in grams over GFM for N, we would get PV equals grams over the GFM times RT. Now we know density is going to be, grams per some volume. So if I wanted to rearrange this equation to get grams over volume, well, let's see, I would have to times GFM over there. To cancel it out over here, I'd have to divide both sides by volume. I'd have to divide both sides by RT. Volume cancels out. So a bunch of obnoxious math, but what I end up with is grams per volume is going to equal the molar mass, which I'm going to put capital M, times the pressure over RT. Right, because the volume cancels out over there. So we end up rearranging and we get this. Density equals pressure times the molar mass divided by RT. So that's going to be our equation that links molar mass and density for a gas together. So using that, here's an example problem. What is the density of methane, CH4, at 700 torr and 120 degrees Celsius? So again, they're asking us to find for the density, and they tell us the pressure, they tell us the, R is a constant, they tell us the temperature, and this molar mass, they give us indirectly by telling us the compound. So we know all those things. So it's really just, all right, density equals the pressure, 700 torr, times the molar mass. Well, I can do the math to figure out CH4. Its molar mass is 16.05 grams per mole, and then divided by RT. So we want to use the gas constant that is in terms of torr, which is 62.36, and the units on that are liters times torr over mole Kelvin. And now the temperature, 120 degrees Celsius, this has to be converted into Kelvin. So we add 273 to it, and we end up with 393 Kelvin. So now when I do this math, let's check out the units. Torr and torr cancel out, moles and moles cancel out, Kelvin and Kelvin cancel out, and I'm left with grams over liters. So that's how I can check that I did my setup right. And when I do the math, I end up with 0.458 grams per liter. Not too bad. Well, what about a similar but different question? Which of the following gases would have a density of 0.9 grams per liter at STP, which is standard temperature and pressure? So the temperature is going to be 273 Kelvin, and the pressure is going to be 1 atmosphere. You could use the other units for pressure, but I like using atmosphere because it's 1. All right, so what we're really trying to solve for is this molar mass, so we can see which one of those has a molar mass that will give you a density of 0.9 grams per liter. So let me do a little rearranging. I got to get molar mass by itself, which means I got to multiply each side by RT. So I get RT over there, cancels out here, and then divide each side by pressure. So that pressure cancels out, and I'm left with the molar mass equals the density times the gas constant times the temperature divided by the pressure. So now they've told me all this information, so I just plug it in. I get 0.900 grams per liter times the gas constant. Well, if I want to use atmospheres, I got to use the gas constant that is in terms of atmospheres. So it's 0.08206. And the units on that are going to be liter atmosphere, liter times atmosphere, divided by mole Kelvin. And then the temperature at STP is 273 Kelvin. And then I divide it all by the pressure. Again, this is one of the reasons why I like using atmospheres when I got a choice with STP. So I just check my units. Atmospheres cancels out. Kelvin cancels out. Let's see, liters cancel out. And I'm left with just grams over moles, which is my molar mass. Awesome. So now I just plug and chug, and I get roughly 20.2 grams per mole. So now I just look at my options and go, which one of these has a molar mass of roughly 20.2 grams per mole? So if I do the math for this, I get CO has roughly 28, N2 is also roughly 28, and O is roughly 30 grams per mole. CH4 is like roughly 16, but Ne, neon, I look up, and its molar mass is roughly 20.2. So correct answer would be neon. So summarize. Can you apply the ideal gas law equation to solve for the identity of gas based on its density and vice versa? I hope so. Okay, bye.